Hello everyone, welcome back to my channel. So in this video, we shall start learning about the main important concepts in the field of chemistry, that is spectroscopy. And here we shall apply the concepts of spectroscopy, especially for the elucidation, especially for the analysis of organic compounds. That means we are going to learn about organic spectroscopy. First, we need to understand what is the exact meaning of the term spectroscopy. Spectroscopy is simply an interaction between the matter with electromagnetic radiation. So when electromagnetic radiation is passed on to the matter, the changes in the energy, that means when radiant energy is or when electromagnetic radiation is passed on to the matter, the light may get absorbed and may get emitted by the material, may get emitted by the atoms of the material. And it is believed that the radiant energy which is emitted by the material is mainly because of the fluctuation of electric charge and magnetic field present around the substance. And by measuring the radiation emitted by the material upon exposure to a electromagnetic radiation and recording the absorption wavelength of the material, the changes in vibrational energy of the molecule, the changes in rotational energy of the molecule, it is possible to elucidate the exact molecular structure of the compound. And that's why spectroscopic technique is very much useful and it is very much helpful in determining molecular structure just by using a suitable instrumental technique. But one doubt may comes into our mind. Why we should only use the spectroscopic technique for the elucidation of structure of a molecule? Why can't we go with some other method like X-ray diffraction, like this? So in order to know what are the main advantages of the spectroscopic technique in determining and identification of a substance, determination of structure of a substance, that should be known to a particular person. So now we shall see what are the main advantages of spectroscopic methods in structural determination as well as in identification of the substance. In brief, let us see what are the main advantages of the spectroscopic method in determining the structure of a particular substance. Firstly, if you have a particular substance, a sample, and if you want to know the exact structure or if you want to identify that substance, we have to analyze the sample, that what we have obtained in a particular chemical reaction. And if you compare the remaining methods, by using the spectroscopic method, the analysis of the sample requires very less time. Very less time is enough for analyzing the sample material. As well, after analysis, whatever the results we get, whatever the information we get, and all those results or information regarding that particular sample can be easily recorded in the form of charts. That is the very first advantage of spectroscopic technique over other methods. Secondly, very small quantity of sample is more than enough for analyzing the sample. Usually, if you want to analyze, especially through volumetric or titrometric or whatever it may be, by conventional methods, if you want to identify a particular substance, we need to take some larger increments of the sample. But in spectroscopic technique, it is very much less sample is enough for performing analysis of that particular sample. In practically about 1 milligram of sample is more than enough for the process of analysis of the sample so as to get the detailed information about that particular sample. So that is the second advantage. Now, thirdly, after analysis, what the results we will get about that sample, those results are highly reliable and most accurate results will be obtained for a particular substance. So since we are getting much accurate results, perfect analysis of a material, a sample is possible so that there will be no errors, so that easy analysis is possible. That is about the third advantage. Nextly, In general, by using conventional methods, it is possible to analyze the neutral compounds or most stable ones. But the short-lived species such as reaction intermediates, say carbocations, carbanions, free radicals, all these components, in particularly carbenes also. So all these reaction intermediates cannot be analyzed by using conventional methods. But by using the spectroscopic technique, even a very short-lived species like carbenes, free radicals, can also be analyzed and their structure can also be identified by using spectroscopic technique. That is one major drawback that we may face during the analysis of a compound is when you subject a material for the analysis, if any changes in the temperature, pressure, or if you are performing a reaction, there is a possibility of a material to undergo chemical changes or they may undergo some decompositions also. But if you subject any sample for the spectroscopic technique, then there is no chances of chemical changes. So the sample will remain intact, will remain undisturbed, will remain unchanged. So a detailed as well a clear-cut information will be obtained for a material by using this spectroscopic technique. That is one important feature of the spectroscopic techniques, and this particular concept is applicable for all the spectroscopic technique except mass spectrometry. So that's the major advantage of spectroscopic technique. And should remember the concept what I said, that the material will not undergo any kind of chemical changes or decomposition, is applicable for all the spectroscopic technique except mass spectrometry. When the analysis is performed so continuously for a compound, the rates of the reaction can also be determined. So these are some basic advantages of spectroscopic methods over other methods. But what is the main principle behind this spectroscopic technique that we need to understand? And now we shall see about the principle of spectroscopy. So if you come to the case of principle of spectroscopy, so when you consider a light radiation of any wavelength, when it is passed on to a organic compound, a unknown compound actually. So when you pass the radiation onto the sample, then the phenomenon that occurs in a material is the electrons that are present in the atoms of the components will get excited. This is the first thing that is possible when the radiation is passed on to a material. And along with electronic excitation, in addition to the electronic excitation, there occurs changes in the vibrational energy of the molecule. There occurs changes in the rotational energy of the molecule, and there occurs changes in the translational energy of the molecule also. But compared to the changes in the electronic energy, vibrational and rotational energy, the translational energy is so much negligible. So we used to consider only the changes in the electronic energy because of excitation and de-excitation of the electron, and changes in the vibrational energy as well changes in the rotational energies of the molecule. And the changes in electronic energy, vibrational energy as well as rotational energy of the molecule as a whole are quantized, means they are independent to each other, and this rule is actually called as Born-Oppenheimer approximation. I repeat, the interaction of the compound to the electromagnetic radiation causes changes in electronic energy, vibrational energy as well as rotational energy, but the changes in each energy is independent to each other. That is called as Born-Oppenheimer approximation. That is, any wavelength of light that a particular molecule will absorb is mainly due to the changes in the electronic energy, vibrational energy as well as rotational energy levels permissible for its atom. And whatever the wavelengths of radiation that is absorbed by a molecule will be measured with the help of a spectrometer. And by the data what we recorded in spectrometer, the molecule will be analyzed. by plotting just the changes in the absorption of the light by a material against the wavelength at which the absorption is occurred. So we used to get certain absorption bands which are highly characteristic of a compound, and the technique provides an excellent tool to ascertain the molecular structure of an unknown substance. So in order to get the information about a material, depending upon the type of radiation we are going to pass onto the sample, into the sample, we are having different kinds of spectroscopic techniques. That means if you pass UV or visible radiation onto the sample, we used to get UV or visible spectroscopy, since it causes changes in the electronic energy. So UV visible spectroscopy is also called as electronic spectroscopy. And if you pass IR radiation onto the sample, that causes changes in vibrational energy. So IR spectroscopy is also called as vibrational spectroscopy. And if you pass any radiation onto the material or radio waves, that gives us very excellent tool that what we call as NMR, that is nuclear magnetic resonance spectroscopy. So these are the three major types of spectroscopic techniques. Still we have like mass spectrometry is there, NQ or nuclear quadrupole resonance spectroscopy is also there. But let us see about UV visible, IR and NMR spectroscopies one after the other. So firstly, we shall consider UV visible spectroscopy, which is also called as electronic spectroscopy. Let us discuss about the first and foremost method of organic spectroscopy, that is UV visible spectroscopy. And this UV visible spectroscopy are majorly called as ultraviolet spectroscopy. It is a type, or it falls under the category of absorption spectroscopy, because here we are going to observe how much of radiation is absorbed by the sample. In a strictly speaking way, how much of UV or visible radiation is absorbed by a material, so as to show the absorption bands. That's why we call UV visible spectroscopy is a absorption spectroscopy. And the absorption of light by a sample either in UV or visible region is majorly occur between the range of 200 to 800 nanometer range. So in this range only the radiation will be absorbed by the material, so as to get UV visible spectrum. So UV visible spectroscopy involves, or else let me say in this way, when UV or visible radiation is passed on to the sample, the electrons that are present in the sample will absorb the radiation and get excited to the higher energy level from ground state. And this reason why UV visible spectroscopy is also called as electronic spectroscopy, as earlier said, since it involves excitation and de-excitation of electrons, and that gives the changes in the electronic energy of a molecule, and that's why UV visible spectroscopy is also called as electronic spectroscopy. And for recording the UV spectrum, the compound or the sample is supposed to be dissolved in a suitable solvent, provided the selection of the solvent is should be done in such a way the solvent is not supposed to show any kind of absorption in this wavelength range. Only such a solvent should be selected for dissolving the sample. For that purpose, usually the solvents that are going to consider is either 95% of ethanol or N-hexane or water. So these three solvents will be used for preparing the solution of the sample. And once the sample is prepared, the sample will be exposed to the UV visible radiation, and the spectrometer will measure the wavelength of the maximum absorption of the light as well as the intensity of the absorption. That means when you pass UV visible radiation onto the sample, absorption will occur by the material. But absorption will occur at all the wavelengths, but the maximum absorption of radiation will occur at one particular wavelength of the past radiation. And the wavelength of the light, which is corresponding to the maximum absorption by the substance, is simply called as maximum wavelength of absorption, which is simply indicated as lambda max, which can be defined as the wavelength of light corresponding to maximum absorption by the sample. That is the simplest definition we can give for lambda max, that is called as wavelength of maximum absorption. And I said when the light is or UV visible radiation is passed on to the material by using the spectrophotometer, it is possible to measure lambda max, that is wavelength of maximum absorption, as well as it is possible to measure the intensity of the absorption. And the intensity of the absorption corresponding to this maximum absorption of light is simply called as molar extinction coefficient. Molar extinction coefficient, which is simply represented with a symbol epsilon, as a symbol for molar extinction coefficient, which will give information about intensity of the absorption corresponding to the maximum absorption of light, that is lambda max. That is some basic stuff pertaining to the UV visible spectroscopy. And now we shall see what is the principle behind this UV visible spectroscopy. So if you come to the case of principle of UV visible spectroscopy, in UV visible spectroscopy, as we said, the absorption of radiation in the region will occur, that is, if you come to the case of principle of UV spectroscopy, the absorption of radiation will occur in the region of 200 to 800 nanometer, which leads to promotion of electron from the low energy molecular orbitals, that is the highest occupied molecular orbitals, that is HOMO, to the high energy vacant molecular orbitals, that is lowest unoccupied molecular orbital, which is simply abbreviated as LUMO. That means when UV or visible radiation is passed on to the sample, the electronic transition will occur by the absorption of radiation will be from HOMO to LUMO. So the amount of radiation which is absorbed by the molecule is actually depends on the overall structure of the molecule, as well the wavelength of the radiation that what we are passing on to the sample. These two parameters will actually influences the amount of radiation which is going to absorb by the molecule. And once the absorption of radiation is done by a molecule, measurement of radiation absorbed by the substance at each wavelength will give a structural detail of the compound. This is the main principle behind the UV visible spectroscopy. And I said when UV or visible radiation is passed on to the sample, the electronic transition will occur from HOMO to LUMO, that is from highest occupied molecular orbital to lowest unoccupied molecular orbitals. But we should know between which molecular orbital to which molecular orbital the electronic transitions are permitted and which electronic transitions are not permitted. So if you go to the HOMO, that is highest occupied molecular orbitals, you will be having sigma and pi molecular orbitals, so which will be completely filled with electrons. And if you go to the lowest unoccupied molecular orbitals, you will be having pi star and sigma star molecular orbitals. And along with sigma and pi molecular orbitals in molecule, there will be a non-bonding molecular orbital also. So as a whole, in a molecule, we will be having sigma, pi, n, pi star and sigma star molecular orbitals. So we can show that by using a simple molecular diagram. So let us consider the energy axis. So in HOMO, there will be sigma, pi, now n, and in LUMO, we will be having pi star and sigma star. So these are the energy orbitals that will be present in a molecule. In a strictly speaking way, the molecular orbitals that are present in a molecule. So these orbitals will be highest occupied molecular orbitals, and these two are the lowest unoccupied molecular orbital. And when the radiation falls on the sample, electronic transition will takes place from HOMO to LUMO. And the possible transitions are sigma to sigma star, sigma to pi star, pi to sigma star, pi to pi star, now n to pi star and n to sigma star. So these are the possible transitions that we can expect once the radiation is falls on the substance. But we should know among these transitions that what we have depicted, which are the permitted transitions, that means which are the allowed transitions and which are the disallowed transitions. By knowing that only, it is possible to exhibit the complete graph, the complete spectrum for a molecule. Based on that, it is possible to say about the structural details of a material. And now we shall see which are the allowed transitions and which are the disallowed transitions. Among all these transitions, the possible transitions and the allowed transitions between the HOMO and LUMO are: the first transition, that is sigma to sigma star transition, is permitted. Pi to pi star transition is permitted. N to pi star and N to sigma star transitions are permitted ones. Sigma to pi star is not a permitted one, and pi to sigma star is also not a permitted one. So the allowed transitions are sigma to sigma star, pi to pi star, n to pi star, n to sigma star. These four are the permitted, or in a strictly speaking way, the allowed transitions between HOMO and LUMO. That is, the allowed transitions between HOMO and LUMO molecular orbitals once the substance is exposed to the UV radiation are sigma to sigma star, pi to pi star, n to pi star, and n to sigma star. So these permitted electronic transitions between HOMO and LUMO. And now we shall see about the individual transitions. Firstly, let us consider sigma to sigma star transition. And this sigma to sigma star transition will occur in the compounds that contains only sigma bonds and there are no lone pairs or no pi electrons. That means sigma to sigma star transitions will occur in case of only the compounds that are completely saturated. And in order to carry out the sigma to sigma star transition, greater amount of energy is required, provided the energy difference, that is delta E, between the HOMO and LUMO is supposed to be greater than or equal to 712 kilojoules. This much of amount of energy is sufficient to make or to cause a transition between sigma to sigma star. And the maximum absorption of light by the substance may occur for this sigma to sigma star will be either less than or equals to 150 nanometers. That is for sigma to sigma star transition. And sigma to pi star transition is not a allowed one. So we shall go with pi to pi star transition. This type of transition, as the name itself telling you, pi and pi star. So this type of transition occurs in only unsaturated compound. That means containing both carbon-carbon double as well as carbon-carbon triple bonds. Okay, so in compounds that containing double and triple bonds as well as the aromatic compound which are containing conjugation will also interacts or will reflect pi to pi star transitions. So best example for this pi to pi star transitions is alkenes, alkynes, all the carbonyl compounds, cyanides as well as azo compounds. All these will give the pi to pi star transitions. And this pi to pi star transition requires less energy than the sigma to sigma star transition, but the wavelength will be little higher. For this pi to pi star transition, the amount of energy required will be less than 712 kilojoules. So less than 7, if it is greater than or equal to 712 kilojoules, that causes sigma to sigma star transition. In order to cause pi to pi star transition, the energy required will be less than 712 kilojoules, and the maximum absorption of light will occur for this pi to pi star transition for a wavelength between 170 to 190 nanometers. In this range, the maximum absorption will be occurring. Now, let us move on to the next two allowed transitions, that is n to pi star and n to sigma star. So now let us go with the n to pi star transition. Now let us go with the third allowed transition, that is n to pi star transition. So as the transition itself is showing, there is a pi and there should be n, that is non-bonding electrons. Cause n to pi star transition, the electrons of unshared pair of electron which are present on the hetero atom will take transition to the pi star, that is antibonding molecular orbitals. So the saturated aldehydes that shows that having a unshared pair of electrons on oxygen atom will show n to pi star transitions, and this type of transition requires a less amount of energy out of all the transitions. That is, in order to cause this n to pi star transition, the energy required will be approximately 450 kilojoules, and the corresponding lambda max for this transition will be approximately equals to 280 nanometers. That is for n to pi star transition. So the name itself telling you n and sigma. Sigma means the saturated one, and along with that there should be a non-bonding electrons. In n to sigma star transition will actually occur in case of saturated compounds that are containing at least one heteroatom with unshared pair of electrons. Mean the saturated alkyl halides, saturated alcohol, saturated aldehydes will exhibit this n to sigma star transitions, and comparatively less energy is required for this n to sigma star transition compared to that of sigma to sigma star transition. So in order to cause the n to sigma star transition, the amount of energy required will be less than or equal to 628 kilojoules, and the corresponding lambda max, that is wavelength of maximum absorption, will be between 185 to 200 nanometers. So this is the wavelength as well as the energy factors that are needed for the allowed transitions, that is sigma to sigma star, pi to pi star, n to pi star, and n to sigma star. To better understand the concepts of organic spectroscopy, we need to know some basic terminologies. So that we shall see now. The first one is chromophore. So chromophore in the sense, if you consider a sample, whatever the structural unit that are present in a sample, and that structural unit which absorb the radiation in the UV region and is responsible for imparting color to the compound are simply called as chromophores. So we can write the definition for a chromophore. The structural units which absorbs radiation in the UV region and are responsible for imparting color to a compound, they will be called as chromophores. And if you want to give some simple examples for chromophores, will be the compounds that is containing carbon-carbon double bond, carbon-carbon triple bond, or conjugated dienes such as 1,3 butadiene. So these things, conjugated dienes, or polyenes, or alpha-beta unsaturated carbonyl compounds, all these things will come under chromophores. So next is auxochromes. So auxochromes are the groups which are not themselves acting as a chromophore, but when they present on the chromophore, they alters, they enhance the color importing properties of the oxochrome. Or in some other way, when a oxochrome is present on the chromophore, the presence of oxochrome will create a new chromophore so that the absorption band, the lambda max of that particular chromophore will get altered. That means there occurs a shift of the lambda max of chromophore either to the shorter or longer wavelength side in presence of an oxochrome. So best examples for oxochromes will be all the functional groups such as the alcoholic group or the ethereal group, an amine that is NH2, or it can be a amide that is NHR, or it can be a tertiary amine NR2, or it can be a thiolic group, whatever it can be. All the functional groups will come under the category of oxochromes. So a simplest definition we can give for oxochrome will be the groups which are not themselves chromophores, but when attached to a chromophore, we will enhance the color importing properties of the next factor is bathochromic shift, which is also called as red shift. So as we already discussed about the oxochrome, that is the group which will alter the lambda max of the chromophore molecule. The change in oxochrome in the molecule or change of solvent, if shifts the absorption maximum, that is lambda max, towards the longer wavelength side, which is due to absorption of lower amount of energy, such a shift is called as bathochromic shift, or which is also called as red shift. So for example, if you consider N2 sigma or N2, if you consider N2 pi star transition for a carbonyl compound which experiences red shift when polarity of the solvent is changed, or else if you consider the benzene, which is a perfectly aromatic compound for which the lambda max is equals to 255 nanometers, but if any one of the hydrogen atom present on the benzene ring, if it is replaced by one oxochrome molecule, that is, say, let me consider the hydroxyl group, then the lambda max of this molecule will become 270 nanometers. In the same way, if you go with the other oxochrome, that is NH2, for which lambda max is equals to 280 nanometers. So you can notice over here, as you move from benzene to phenol and phenol to aniline, lambda max value is getting increased. And this is mainly because of increase in the resonance in the molecule. So compared to benzene, in phenol resonance will be higher, and in aniline the resonance will be much more higher. Because of this reason, the lambda max of the components is continuously increasing, that is, it is shifting towards the longer wavelength side, and such a shift in the lambda max of the molecule towards the longer wavelength side is called as bathochromic shift or red shift. Next it is hypsochromic shift, which is also called as blue shift. So in previous minute we said presence of an oxochrome or due to external factors such as temperature or solvent, if the lambda max shifts towards the longer wavelength side, that will be called as bathochromic shift. If it is exactly the opposite, that means if change in oxochrome or change in the solvent shifts the lambda max of a chromophore towards the shorter wavelength side, such a shift in the lambda max towards the shorter wavelength side is called as hypsochromic shift, which is also called as blue shift. If you consider aniline, in which oxochrome is NH2 and chromophore is benzene, so for which the lambda max value is 280 nanometers. But when this aniline got protonated, you will be getting anilinium ion. That means the lone pair of electrons present on the nitrogen atom will receive this H plus, and that results in the formation of NH3 plus. And if you check the lambda max value of this anilinium ion, it will be appearing to be 250 nanometers. You can notice there is a decrease in the 30 nanometers of absorption wavelength. And here you can notice Compared to benzene, benzene will show a absorption maximum at 250 nanometers, but aniline will show at 280 nanometers, which is due to increase in the resonance of this pi bonds that are present in the benzene with lone pair of electrons present on the nitrogen. But when aniline is treated with an acid, which is H+, formation of anilinium ion will lapse the presence of the lone pair of electrons on nitrogen. Therefore, there will be lapse of resonance of benzene with the lone pair of electrons. So decrease in the conjugation, decrease in the resonance will reduces the absorption maximum of the molecule, which can be observed with the lambda max values which are given for aniline and anilinium ion. So here you can notice the reduce or shift in the lambda max value towards the lower wavelength side is simply called as hypsochromic shift or blue shift. Now we shall move on to the next term, that is hyperchromic effect. Sometimes the presence of certain groups, that is oxochromes, or by some external effect, that is the change in solvents or temperature, the intensity of the maximum absorption, that is epsilon max, if it get increases, such increase of the intensity of absorption is simply known as hyperchromic effect. And a hyperchromic shift, that is increase in the epsilon max, can be observed when to the paranitrophenol. So here we are having phenol, right? So phenol is the oxochrome. So nitro group is present at para position. If to this paranitrophenol, which is more acidic in nature actually, so when to this acidic material, when you add a base, that is a alkali. So when you add alkali to this paranitrophenol, then the intensity of the maximum absorption will get increases, and such an increase in the epsilon max, that is molar extension coefficient for the lambda max, that is wavelength of maximum absorption, such an shift or such an effect is called as hyperchromic effect. We said in case of hyperchromic effect, the intensity of maximum absorption will get increases. If you come to the case of hypochromic effect, the presence of certain groups or by some external factors, certain effects, if the intensity of maximum absorption, that is epsilon max, if it get decreases, then such a decrease in the intensity of the maximum absorption is simply called as hypochromic effect. So you can observe this hypochromic effect when N comma N dimethyl aniline, N comma N dimethyl aniline. When this N comma N dimethyl aniline is treated with an alkyl halide, that is methyl iodide, which finally results in the formation of quaternary ammonium salt. And this formation of quaternary ammonium salt will decreases the intensity of the N comma N dimethyl aniline, and that decrease in intensity is simply called as hypochromic effect. So these are some important factors that are supposed to be understood with respect to organic spectroscopy, that has to be understood. These are the factors, these are the terminologies that are supposed to be remembered while dealing with UV visible spectroscopy. Let us see the effect of conjugation on lambda max of the molecule. The wavelength of absorption will be shifted to higher values, that is we can see the bathochromic shift if two or more chromophoric groups are in conjugation in a molecule. So if you consider ethylene, that is CH2 double bond CH2, which is having one carbon-carbon double bond, so which will be having a absorption maximum, that is lambda max, at a value of 170 nanometers. And this lambda max value is mainly because of pi to pi star transition which will be observed by the molecule. But if you consider this one, that is 1,3 butadiene, which consisting of two double bonds, that two they are present at alternate position, that means they are conjugated to each other, and this 1,3 butadiene will show lambda max at a value of 217 nanometers. So like this, when a material is extending its conjugation, the lambda max value is also getting increases. That is, the bathochromic shift is more pronounced if the double bonds are in conjugation when compared to their isolated, means the double bonds are present at extreme ends. So bathochromic shift is highest in case of conjugated double bonds. We should know what is the main reason for increase in the lambda max value of a material with increase in the conjugation. The actual logic behind this is, as the conjugation increases, the electron density will spread over at least 4 atomic centers. So let us consider this 1,3 butadiene only. So CH2 double bond CH single bond CH double bond CH2. So here 1, 2, 3, 4, we are having 4 carbon atoms. So the electron density will be spreading like this between all the 4 carbon atoms. So wherein the 2 double bonds are in conjugation to each other. And because of the spread of electron density over multiple atoms will increases the energy of the highest occupied molecular orbitals, that is HOMO. And simultaneously, the energy of the LUMO, that is lowest unoccupied molecular orbitals, will get increases. As a whole, the energy difference between HOMO and LUMO, that is delta E, will get decreases. So when there is a less energy gap between HOMO and LUMO for a molecule which is having conjugation, less amount of energy is enough to cause transition of electron from HOMO to LUMO. We know that from Planck's quantum equation, E is equals to h nu, or nu is equals to c by lambda. That is, E is equals to hc by lambda. That is, energy and wavelength are inversely proportional to each other. That means with the decrease in the energy, obviously lambda value will increases. So that we can clearly say, since very less amount of energy is enough to cause electronic transition from HOMO to LUMO, in case of conjugated system, the wavelength of the radiation should be higher. So that we observe increase in the lambda max value, that what we simply call as redshift or bathochromic shift. So as a whole, what we can say, with increase in the conjugation, the lambda max value will increases, that we observe bathochromic shift. So let's see the comparison of lambda max value of acetone, which is having the formula CH3C double bond OCH3, with that of methyl vinyl ketone, which is having the structure CH2 double bond CH C double bond OCH3. This is acetone and this is methyl vinyl ketone. When you pass UV visible radiation, on to the samples of both the materials, in acetone we are having only carbon oxygen double bond as well carbon carbon single bond. So we can notice only one electronic transition corresponding to N to pi star. So that the lambda max value will be observed for acetone at a wavelength of 270 nanometers. But if you come to the case of this methyl vinyl ketone, here we have both carbon-carbon single bond, carbon oxygen, as well as carbon-carbon double bond. So in case of methyl vinyl ketone, along with N to pi star transition, because of presence of pi electron density, there will be a pi to pi star transition also. And because of both of these transitions, the lambda max value of methyl vinyl ketone will be observed at 320 nanometers. So we can observe the bathochromic shift between these two molecules. Okay, so this is how the spectra of acetone and methyl vinyl ketone can be expressed.